This is a short introduction to real solutions and activities. So far we have only looked at ideal solutions or ideal dilute solutions. But in most biological systems this is not the case. The cell is a crowded environment and almost nothing in the cell is 50 nanometer away from a membrane or an intracellular organelle. So cell solutions are typically real solutions. So we'll look at how we do the math for a real solution. We have shown that the chemical potential of the solvent is given by, in a mixture, is given by the chemical potential of the pure solvent plus RT logarithm of the partial pressure of the solvent in the vapor phase divided by the vapor pressure of the pure solvent. Now this applies for any solution, whether ideal or not. If you have an ideal solution, then the mole fraction of the solvent in the liquid phase is equal to Pa by Pa star. And this equation becomes logarithm of the mole fraction of A. If the solution is not ideal, then Xa is not equal to Pa by Pa star. So we introduce a new quantity called the activity of the solvent of A, such that the form of this equation remains preserved. So now the chemical potential of the solvent becomes some chemical potential of the pure solvent plus RT logarithm of what is called the activity of A. For an ideal solution, activity of A is equal to the mole fraction. As the mole fraction of the solvent tends to 1, you go towards a dilute solution, which is more likely to be ideal, and therefore the activity approaches the mole fraction. To quantify this convergence of the activity to the mole fraction, we define another quantity called the activity coefficient. This is denoted by gamma, and this is equal to the activity divided by the mole fraction. And you can see as the activity approaches the mole fraction, so the activity coefficient approaches 1, which means that for ideal solutions, the activity coefficient is equal to 1. So this was for the solute. You can similarly show that for the solvent, and we are not going into the details here. The chemical potential is the chemical potential of pure solute plus RT times the logarithm of the activity of the solute. Now this form of the equation not only applies to a solute which is in smaller quantities and a solvent which is in larger fraction, but to all components in a mixture. So the activity, there's a certain standard state. The activity of a solid, a pure solid, is always equal to 1. The activity of a pure liquid is also equal to 1. These are under standard conditions. For a solute, the standard condition is 1 mole per liter or 1 mole per decimeter cubed. So for a gas, the activity is typically provided in terms of a partial pressure divided by some standard pressure. So the activity is dimensionless. For a liquid, the activity is provided in terms of the concentration of the substance, we call it J, divided by some standard concentration. This could also be the molality of J divided by the standard molality. In all cases, the activity is a dimensionless number. And just to repeat, in case of gases, it is the partial pressure. In case of liquids, it is the concentration. For pure solids, the activity is always equal to 1. All this information is contained in table 3.3 in your text in Atkins. In the next video, which will be also uploaded soon, we will see how we can write the reaction Gibbs free energy in terms of the activities of the individual components of the reactants and products in a reaction.